Okay.
Great.
Okay, no worries, no worries. I will start with a short recap. So usually I go very quick through what I did last time. And so that you can also ask questions. Oh, I didn't understand this or that. So I last time. Oh yeah, camera. Yes, thank you very much. So last time I will start from here. We introduce the concept of a group, which is the simplest algebraic structure you have in mathematics, basically. And then, you know, if the group is commutative, like what, for example, real number multiplication, if you leave the zero out, or the sum with, you know, the sum of integer real numbers, it's also a group that is also commutative, but matrix multiplication, for example, is not an abelian group. And then you can define and refine add extra structure, and you could go to what are fields like, for example, real numbers. Real numbers is, for example, is a group in sum, as a sum. Real numbers, you know, the field has two operations, a plus and a multiplication, and the field has, for example, is a group in plus, and is a group in a multiplication if you get rid of the origin. Okay, and has certain property of distribution of the plus and the multiplication. That's what a field is. And this, my example of the field you use every time are real numbers and complex numbers. For example, there other fields are also, of course, very common in mathematics. And here were some links which I found very interesting. That this is the definition of the group. The group only has to satisfy these three properties. These three properties. So you see, it's a first algebraic structure in the sense it is a map. Everything is mathematics. It's the basis. You have sets and the maps between sets, and this is an operation on M, which can be written as, you know, a binary operation on two objects beside. It's just the way you define it. This is just to be a bit more precise. And the most important, this is an associative property that needs to be satisfied, identity, and inverse. These are the three things that a group is satisfied, okay? And the fact that in multiplication of real numbers, you have to get rid of the zero. Otherwise, you don't have an inverse of zero. Zero cannot be an element of the set, like a non-singular matrix cannot be an element of the matrix multiplication set. Okay? And I gave this example. And then what we also have seen is, you know, what is the the important, if you have a map between sets, you have no other structure. You know, the thing you can talk about the map is, you know, are these three things we indicated as surjective, injective, bijective. You cannot say anything else. But if you talk about a map between two things which are not only set, but they are groups, and they can do something here, something here. The question is, does this map preserve these operations? And if you start getting the logic, you could have written down what the homomorphism is, because it's the only thing you can do. You cannot do operation on the left. You can do operation on the right. What is the obvious things to do? It's written there. Okay. Then and now an example is this. So we use it all the time. This is in engineering very common. You know, exponential logarithm is basically creating this isomorphism in between these two, with R plus with the multiplication and R. And this is very, very useful. And a lot of things in engineering and mathematics come out from this. Okay, the exponential is one of the most amazing functions in all of mathematics, by the way. Then we started talking about vector spaces, okay? And then I played this game. I will not play again. Which I show you that matrices are not really mathematical objects, but are a representation of something that you will see today, which are tensors. Tensor is the real mathematical object. What is a vector space? A vector space is a triple, three things. So you cannot say Is this a vector? If you just give me an element, excuse me, in a set, I cannot say whether that is a vector or not. If you give me, you know, I draw this and I say, is this a vector? Not well posed question. Okay, that's not a vector. It says, okay, give me what are the sets and what are the operation you can build. What the operation is, I tell you how to sum this doing the parallelogram rule. Okay, I have an addition. I tell you how to scale these things. Oh, I have them. And if they satisfy the axioms which are repeated here, then it's a vector space. But you cannot say, is this a vector? It's not actually a well-posed question, okay? And of course, you do it all the time, but you should be aware about that. Okay, and then there are certain properties which are very important, so which are called Kani-Adu, which are, you know, certain distributive properties and associative and other things that you have seen, and you can go in and search for the details. So the important thing here, which is the core, which is done implicitly again and again, wrongly also by good scientists, is the realization that a pure vector space does not have any length, that does not in the product, does not have any orthogonality, angle, nothing. Okay, so and a lot of books start with saying a vector space. What are vectors? Vectors are objects that you can sum and they have a length. Bullshit. They don't have a length. Okay? There is no measure of length. Very important. It will all come up with a structure that we'll introduce, which is called an inner product. And we get from a vector space, and adding this structure, we get with something which is called a Hilbert space, okay, which basically has a vector space with an inner product satisfies certain properties, and then an whole world opens up, which is what normally is implicitly chosen. But in robotics, you have a lot of situations where this is not the guy you think it is. So it's important to be very precise. Okay. And so these are some examples of vector spaces. And then same game. So now we say, okay, you know what vector space is? What is vector space? Where the triple vector space is a set plus multiplication. Three things. Okay. And then you have another vector space here, a different vector space, different set, different plus, different multiplication. And then you have the map between the sets. And now the question is, you know, you can define any map. I don't care. You know, it's a free world. Any map. But then, what is a map? What are the kind of maps which keep the structure? What are the kind of map that means operation here are the same as the operation here, right? And then you could write it down because you know what the operations here. What are the operation of a vector space? Linear combination. That what these two things gives you is linear combination. That's it. Okay. You can sum vectors and you can multiply for a scalar. So if you take the most general operation, means you give me a bunch of vectors, I multiply for a bunch of scalars in the field that you are using, which in our case is real, but could be complex if you have a complex vector space, and you sum them, and you get a new vector. That's it. Okay, now the question is, if you map this on the other side, do the same linear combination. So it's obvious that you have what is indicated here, right? And this is structure preserving. A structure preserving map of linear spaces, of vector spaces, are linear maps. Okay? And then the question is, everything I said is abstract. Okay, you don't need to talk about numbers at all. You know that you can say you have elements in this vector space, you have operation, you define the operation, etc., etc. Okay? And then the question is, what is if at a certain point you want to go to numbers, if you have you want to do calculations. So what can you do? You choose a basis. What does that mean? Well, a basis is basically you choose a number of elements in that vector space, which basically can generate any other element by proper linear combinations. That's the idea. Okay, which is the frame. You know, this vector. If I take a vector space with the origin where it's here, then I say this and this and this, or this and this and this, as long as they are linear independent. For this, what is the basis, can generate the whole vector space. Okay. Okay. And in finite dimension, I will use this. I will skip this. We'll use this notation again and again. I'll skip this slide for the time being. What then we can get to, and this is the important thing, is all right. Now we have talked about linear spaces. Now what? I can define as a vector space a vector space with plus and multiplication. As the vector space I map to, I can choose R plus and multiplication, which is a vector space. Okay, so it's just a linear map in which the space I go to is just real numbers multiplication times. The set of all these linear maps like this are called linear functionals on V. Okay, that's just the name, linear functional of V. So, for example, if I give you, you know, in what you do all the time, if I give you a column vector, and you want to go to a real number, if this is a vector space, you define multiplication and sum as you do. This would be something you can multiply for, you get a real number, okay? And it's linear, clearly, because it's a matrix, okay? But of course, you could think about something else. You know, what's if distributions? If I give you a function on an interval, okay, and I give you all the possible linear situation in which if you take the integral of this function, it gives you a real number. Okay, that's called a set of distributions on that interval. The delta, for example, function, that's the proper way to introduce it because it's dual to the space of function. A delta, Dirac pulse is not a function, it's a distribution in every sense. All right, and then once you have that, then you can define, this is where we got last time, I believe, right? Then you define the space V star, which is the dual space to V, okay? And this is a finite dimensional case, but you know, at a certain point, I will introduce infinite dimensional situations in a very general way in which you can handle any kind of physics, classical physics. Okay. Quantum physics can also be handled. So this is called the set of all linear operators from V. I just put n as, you know, dimension n, but in general it's true all the time. To R, and it's called a dual space. Okay. And notice this issue is that if I have an n-dimensional vector space, by definition, the previous definitions, it means that there are, I can choose n linear independent vectors that can generate the whole vector space. Now, if you take this n elements, okay, and you chose it in V, then you can uniquely define the dual space. So you can uniquely define other n vectors, but in the dual base. So you see, notice that the notation is something that I will be repeating again and again. You see, these elements have the index down. Okay. So by this note, and these are the E are real vector, let's say abstract vectors. Okay. So if they have the index down, it means they belong to V. If they have the index up as vectors, it means they belong to V star. We will see that the linear combination would be the opposite. I'm coming there later. But what it means that these guys here are linear operators, on element of V. So if I can take one of these linear operator and apply on a vector. Okay, because by definition is a guy like this. So I can feed him a vector and he returns a real number. Okay. And this base is defined such that if you take the first element of the base of the vector, okay, then any other element of the dual base will return 0 if they are different, and will return 1 if they are the same. Okay, and this notation is just a notation which is used, for example, in quantum mechanics, which basically says the pairing between a vector and a covector. Okay, it's just a notation. I define this as this. Okay.
En waar doe je even tussen en integral book?
This is just to indicate that the dimension is n.
Dimension is n. Okay.
Yes, only for that. Yeah. Any other questions? Okay, so this is this is the so it's always possible. So in other words, well, we'll come to an example later. So this is just the definition. So if I choose n element in the vector space, there are n element in the dual vector space, and they are not in the same space. You see, V and V star are different things. Okay, physically speaking, what is done wrongly all the time is that when you talk about mechanics, for example, then you say the force is a vector. It's not. You know, the force is a vector, but belongs to the dual of velocities. It's a different thing. It's a different object. Okay, okay, and then it's not if you take power and you take a velocity and a force, you do not calculate power by taking the inner product. That's wrong. It's just wrong. It's a natural pairing. That's the way you say it. It's a natural pairing between a vector, velocity, and the linear operator from velocities to power, which we call force. Okay, it is not an inner product. It's a natural product. There is no structure. There is no inner product here. Okay, this is the crucial point of everything. Okay. If I give you, and in the notation, I'll come to that later, in the notation that I will use, and this is standard Einstein notation, so physics is all based on this notation, is if I want to write a vector B, for example, a velocity, okay, normally I say, suppose I have element in the basis, okay, so what you normally say, okay, it says that the dimension is 3, just as an example, n is 3, okay? So what you do is says, okay, velocity v, this is the abstract velocity, is the sum. Oh my God, this is always the same story, this guys. I have a new package in case I will be the same. From, this is really gone. They put it back, I think. Where is the rubbish bin?
They're the same.
No, I have them, but I want to be sure that these are thrown away because you know, could you?
Yeah, I will.
Remind me. I will throw it away later because otherwise it's always been there. Yeah. So can you read this? So I goes from 1 to 3. Okay, and then I say B I E I. What does that mean? Well, these guys here are real number. Okay, because it's a real vector space. These are the coefficients that I can multiply one of the two operations I have, right? And these are guys which belongs to V. Okay, so this would be, well, E1, E1, E2, E2, E3, E3. You see? This is, I'm using the operation of the vector space. I multiply by a scalar and I sum the vectors. And this is what we do all the time. Linear combination can be representing any vector as a combination of the bases. That's it. No more, no less. What the Einstein notation does, it says, you know, in these cases, you always use this sum, so I don't need to write the sum. So when you write something like this, I mean this. The sum is there, it's just I don't write it. If the two letters are the same. If the two letters are not the same, then it's a matrix. There are two indices, different indices. But if I write the same indices, it means this. Okay? Now, notice one important thing. You will see that if I use this basis constant, I use the base and the dual base properly, at a certain point, I don't need to write the easily. And I will only use the V, the representation, as we do all the time, the array of numbers. But if I write the index here up, you will just by looking at that, you see there is one index, so it's an array of numbers. If the index is up, immediately by convention, it is a vector. If I give you a force, on the other hand, a force, okay, would be the same kind of game, but look what happens. I will not write the sum. I want to get rid of immediately. You will write it as F J E J. You see, I invert both indices. Okay, so notice once again, this guy here is a real number. This guy here belongs to V star, as this guy belongs to V star. Okay. And the same is the same story. So this is a real number. I could write F1, etc., etc. Okay, and this is true, of course, for 3, but it's true for 5, for 4, for 100, whatever. Doesn't change. In fact, in quantum mechanics, you can write this as an infinite basis. Okay, so this is And notice that because of this convention that you only remember that you can never sum things which have two indices like this or two indices like this, only this of this, okay, is that for vector, for the numbers represented, the vector, the index sticks up. The basis for therefore should be down. But here is the other way around, you see? So if I now give you an array of number and the index is up, is a vector. If I give you now an array of number and the index is down, is a covector. Why is that is useful? Because now, if I want, and what is in the next slide, I will show you. We'll see in the next slide why that is so important. Because now you will, if you use this base that satisfy this relation, I will show you in the next slide that you can't forget about the bases. We have found a way in which you can indeed use array of numbers as you've always done, but then in an invariant way. You will be able to understand if the operation you do as simple as do something with two array of numbers, if that makes sense or it doesn't make sense. I'll give you an example, something that makes sense. Force on a velocity is something that does not make sense. Two velocities in a product. Okay, so let's look at this. Suppose I have a general abstract linear operator on velocities. Force. Force. In the example, I use the physically. Okay. There exist LIs, which are the real numbers that you can linear combine for the basis, such that I can express any of this like this. It's like in a vector space, but then now in the dual vector space, right? So I can express any linear operator as the linear combination of this. This is what I wrote here. Same story, okay? But now, and what are these numbers? Well, these numbers are such that if I take the linear abstract linear operator, okay, and of course I can apply it to any element of V. Also, therefore, these guys, E1, E2, and E3, right? So that's what I'm doing here. Then it will return that value. So look at what happens here. So take a general, so I know L is a linear operator on V. So I can do something like this by definition. And I know it is linear. So I know that L is a linear operator on V. Okay. So I know that I can express both the vector spaces, right? V is vector space, V star is a vector space. So I can express L as the linear combinations of element in the base. This is what I didn't write it, but it's the same as this, but then for this guy here, okay? Which I basically left the sum out, but that's what it is, what that means, okay? So this is this, and this is literally what I wrote here, okay? But then for a general N. Okay, so this is just definition. You see, I have a linear operator on this. Now, I know that this is a linear operator, right? What does that mean? If this is a linear operator, I can take the sum out of it because it's linear. Okay, so if I take this, you get this. So what you see is this is a number, just a number. You know, I multiply a number. This is a number, okay? And this is a linear operator on these guys. So the numbers, you can get them out because it's all linear. So eventually you get to an expression like this, in which you have the same sum and nothing changed, but just by linearity, I'm left here with the application of this base element on this base element. This is the base element of the linear operator, and this is a base element of the vector space. Okay? But now, by definition, because I chose the dual base satisfied that condition in the previous slide, okay, I say, okay, wait a second. If I is not equal to J is 0, so in that sum, that term doesn't count. Only the counts, because it's a sum, only the things are not 0 if I is equal to J, right? So if, and then it becomes a 1. So when I is equal to J, this becomes a 1. And then I can substitute J and I being the same, because are the only terms that are not equal to 0. And therefore, the sum for two indices become one sum of one index. So then I have the sum in I of this. Then you see that now, by choosing these dual bases, the abstract operation of a linear operator on a vector, abstractly, I have no numbers here, can be represented naturally in any base, because, you know, I just tell you I choose a base and I choose the dual of that base as something like this, which is what you do all the time. Okay. But you see, that is a natural thing. Yes, please.
When you say linear functionals and linear operators, is it synonyms?
The same, it's the same. Well, it's no problem. So linear functionals means that it goes to R. Linear operator is just a linear map. It could be anything else. So so a linear functional is a kind of linear operator. Yeah.
It goes specifically to R.
Yes,
by definition.
Functionals go to R. Yeah. And it's normally used for infinite dimensional spaces, but it's true also for finite dimensional space. So in variational calculus, for example, a functional, you know, you give the Lagrangian, if you, for example, in physics, you know, the action is a base of physics, then you have a functional, but that is not very linear in general, but it's called a function if you go to R. That's basic. Yes.
I think you have called force multiple times covector,
That's correct.
but also multiple times an operator.
Yes.
So you can use those interchangeable.
Yes.
Does it also mean that a vector is actually also an operator?
Absolutely, yes.
On the covector.
Absolutely, yes. Okay, so in fact, this is true for finite dimension. In infinite dimension, there are some tricky things, but still, you know, it's pretty much the same. I'll give you examples later. So if I, you know, in the way you are normally used to, right? So you have a vector, you multiply times a matrix like this, you have a real number. So you can see that this is a linear operator on these guys. Vector, covector, real number. But I could do this, okay?
Yeah.
And then you have that a vector is a linear operator on covectors and give you this. So you see, this is clear, but it's very, very deep. It means they're really dual. Dual means from Latin two. So it's really one way you go in one and the other. There is no third thing. It is a kind of marriage between vectors and covectors, man and wife, duality. Okay, it's very deep, and it's. In fact, I am convinced, and I mean, for classical physics, I've seen it again and again and again. You will see it more and more, how fundamental this duality concept is in nature. I think it's even more fundamental than anything else. And I'll try to convince you with that. So there's always, when you have in physics, you have something, a physical quantity, duality, there is a quantity which is related to that. In a dual setting, you will see it again and again. Okay, this is definitely true for. You will see. I mean, I will stop it for now on that, but I will convince you that that's always the case.
Does even hold if you, for example, if you look at electromagnetic waves.
Yes.
And you can say you have the E and the B vector. There.
Absolutely.
But you can also represent it in the particle domain, photons.
Yes.
So how does this duality
We'll get there.
over to the particles?
We'll get there. We'll get there partially. Okay. I will actually show you precisely Maxwell equation in a way you've never seen, and then you will say, "What the fuck?" I guarantee you, because it's a completely different way to look at this, and it's pretty amazing what you see. So, thanks to this duality. That's something actually I'm working with Fredrik on now, with one of our projects, okay? So I'll show you later, but it's very deep. It's very, very deep. Okay, so this is normally what you do, right? So if I give you a vector, basically the elements which are here are basically the value that you get if you take the linear operator you want to express on the basis that you use in order to express these numbers. Okay, that's basically the idea. All right. Now, yes, please.
Quickly, please repeat why the sum in the end falls away.
From 2 to 1 sum.
Yeah.
Yes. So,
not from 2 to 1 sum, but from sum to no sum.
oh, it's just notation.
Okay.
It's just a notation. So this is just like, oh, okay, I use Einstein notation. So the sum is there. It's just in white ink. You don't see it.
Do you not have to use the double dot then for this, or
Sorry, the double.
like on the board you use like equal?
No, this is the definition. So I defined it already. Yes, of course, if I would say, but I told you already, so it's not a definition anymore because I told you before. Okay. So this is a result now because it's not a definition anymore. Definition, you do it once and then you use it. That's the idea. But so the point is that when you see two indices and you'll see it again and again, and this is all over physics, when you see two indices like this, it means this is now are not two arrays of numbers, it's a real number, which is the result of this pairing. Okay? It's you see it all over physics. So when you see something which is the same letter, it means there is a sum there you don't see about along all the dimension that you have. If it's 3, it's 3, in space-time is 4, and whatever. Is it clear? Yeah. So it's when I write it like this, is actually here is all a bit misleading. This is fine, but here I already used the definition again. You see, because I didn't write the sums. And then I tell you later that there's some other actually there. This is white ink, black ink. You calculate white ink again. Okay. So it's just a notation. It's a convenient, very, very convenient notation. Because otherwise, you would have sums all over the place. It gets very nasty. And when it's very clear what you want to do. Okay. Any other questions?
Yeah.
Yes.
That it can be seen that V star is a vector space with its own operator. You mean, okay, V star is a vector space by himself, so with two operations.
Yes, exactly.
So what should can be seen? I didn't understand.
Well, I mean, if
you mean?
you could then say, you know, how do you define, suppose you have a L1 and L2 here, abstractly speaking. Okay, how do you define that? Well, you define it in a certain way, which is the way we always do. And then you would find that this operation that you call that plus. Okay, but I just to stress that, you know, the two spaces are not the same. And here is a bit difficult to see that they are not the same. But if you go to you know, to polynomials or other things, it's, you know, you have to think about it. But as long as you have the idea clear and you work with this, okay, then you see this always the same. It's a very structured way. And I think is once you understand this game, then sometimes Federico was just coming in with a puzzle. It says, you know, I give you a vector space of polynomials, second order polynomials in an interval. Okay, what is the basis of that? Well, you know, are the coefficient of the monomial 0, 1, and 2. And he was saying, you know, what is the representation of the dual space? Okay, I have to think about it, but I needed to start lecturing, so I didn't think about it. Okay, but this kind of, it's you know, it's just a matter of using the definition, and it's a puzzle you can solve because it's clear. Okay. All right, now here, this slide is the core of everything we have seen so far. Okay, so this is very important, and I'll give you an example. So what you have is now you've learned that if you're giving an array of numbers and you want to do not mumbo jumbo numbers, but you want to do actually express this number are actually physical things or things that do matter how you use them, you know that it's a vector space is actually an abstract thing. And a vector space is an abstract thing. You can, if it's finite dimension, you can define an element in the basis. Okay. So, you know, E1, En, and V are really abstract element in a vector space. And then if you take n real numbers, you can express this V like this. Because you know that if n-dimensional, any n+1 vector can always be expressed as a linear combination of n. That's the definition of a base, right? So this is basically with a white ink, well, blue ink in this case, otherwise you would see it. Sum, okay, is the linear combination of the element in the basis. And notice the index here of the element themselves is down. But these numbers with index up, you recognize is a vector. So if from now on, when I write and you look at physical things written down, if the index is up, is a vector. No doubt about it. Okay. Dually, you have a dual vector space, which is different. So a different thing. It's very, you know, it's like it's connected to that V because it's a space of linear operators on these guys. Okay, but it's by itself because it is linear, also linear vector space, with a certain operation, which I indicated with different symbols to make clear it's not the same operation. Why is not the same operation? It's obvious because it acts on these guys. You know, by definition, a function is defined on something. With this function is defined on these guys. not on these guys. You know, it's mathematically, obviously it's like that. And then the basis of this are n as well. You could prove that formally, but you see I put the index up if they belong to the space. And the number you multiply with, well, I use V here, but in the example there will be the F, okay, the forces. The index should be down, so there's always these things that one up, one down. And this is the core. There is intrinsically, it's a dual pairing. There is no extra structure. There is nothing else. There is no length. There is no inner product. There is no angle, nothing else. If I give you a vector space without anything else, the only thing you can define is a dual vector space. And if you have a dual vector space, then you can give me one of these guys here, one of these guys here, you let them kiss and a real number comes out, okay? There is no way, no structure now, so far, that I give you two vectors and you can return me a real number. There is not. You can't. It's an extra structure. That's called an inner product, okay? And this is messed up all over the place. And I tell you example of gradients also in what is called, you know, what is a gradient, for example, and these kind of things. Again, it's messed up. Is this very clear? This is the core of very simple, but it's a core, okay? Now, just as notation for this, I said it last time, I will repeat it. In quantum mechanics, for example, you see this notation very often. If you have, for example, psi1 and psi2, okay? And indeed, it's precisely what I'm telling you. So this is a bracket, right? And I showed you last time that was a nerdy joke, which is now used in quantum mechanics. Now, this guy here in quantum mechanics is called the bra. And this guy is called the cat. Not because cat of Schrödinger or whatever, it's because this together is the brackets. Okay? And this is nothing else, is what Dirac was used just to tell you explicitly, different kind of notation. This is a vector, this is a covector. And if you take one together with the other, magic appears. But then for quantum mechanics, you get a complex number, not a real number, because we're in a complex field. Same story, okay? So if you now see, for example, Schrödinger equation I mentioned last time, which when I saw Schrödinger equation, I saw this symbol, I said, what is this? Where's my, here. For example, Schrödinger equation, now, if you look after you say Google Schrödinger equation, you'll see this. Okay, you'll see Phi H is Phi dot I reduce Planck's constant. This is Schrödinger equation. Now you see what it is. It's absolutely the simplest equation you can imagine. Okay, what is this? Well, this is a vector. Space is infinite dimensional, but that's a detail. This is a vector. What is this? Again, a vector, right? It's the time derivative of this vector. We do it all the time. You know, if you write x dot is equal to ax, linear system, same story, right? So, and what is this h? Well, this is the same what a is. It's a linear operator. It just is an operator. If this is infinite dimensional, well, this is really an infinite dimensional operator. If you satisfy the linear properties I told you, it is a linear operator. Who cares? Okay, and for spin, for example, you can do it finite dimensional. That's another issue. And this is, you know, that's the fact that here is the reduced Planck constant. It's just a constant with a complex number. But you see, this is a linear equation like this. But then it's Schrödinger equation. It's nothing else than a linear differential equation. Okay. But then you understand the notation. So this is a vector. And if you write in, and then there are other issues in quantum mechanics, this is a covector. Okay. And in fact, because you have quantum mechanics, you have by construction, you don't say that you only have a vector space. You have a Hilbert space, you have an inner product, you also have a way to map natural this to this. We'll get to that later. All right. So why is this important? And now here comes the core. If I give you now a vector space, an abstract vector space, okay, and you choose two bases. So let's say, who has a blue shirt? You. Okay. You choose the places, the blue bases where nobody has this color. Okay, you. Okay, Peter is the orange and you're the blue. Okay. As a free word, you choose your base. You choose your base. And of course, you get the real number representation if you choose your base or your vectors, right? And then there is a matrix that maps from one base to the others. Okay. What are the conditions that the matrix was satisfied if this is really a change of base?
Singular.
It has to be on singular, right? You need to be bijective. You have to go back and forth. Otherwise, it's not a proper change of base, right? Very good. Okay, now let's see what happens if I now, and okay, this is the notation I used before. Let's see what happens now if I want to calculate power. Suppose that now the vector space is the space of velocity of a point mass. Okay. And now I say, good. Well, if you calculate power and you calculate power, you choose your base, guys, you should get the same power, because if you do the calculation and get a different power, there are three conditions. Either he's wrong and you're right, okay, or you're right and he's wrong, or you're both wrong, okay? You cannot be both right if the two powers are different, okay? So now let's see what happens. So I'm saying, oh, that's fine. So I calculate the powers and I write it like this. I don't know anything about what you learned so far, okay? I'm just saying, okay, I have a velocity, I have a force, and if I take what people call the inner product, we know that is wrong. It's a dual product of these two guys. And you get a real number, I want that is the same. Okay, let's use a change of coordinates. I call this change of coordinates A. I had S in the previous slide, doesn't matter, but it's A is the change of coordinates, right? Okay, so I substituted here, okay, because I just substituted there. V is A bar, so that's what you get. All right, now, so it's for every V bar, right? Because I want to calculate it, not, the force can be, the velocity can be anything. So it should be true for any velocities. Okay. Now, how can I do this step? What is that I should do to make that step properly? Why is that true?
What is the question again?
The question is, now I have this equation, and this is true for each V. Can I just cancel? These are vectors, not a scalar, right? That is different than zero. You can just cancel. Why that makes sense? What am I doing here? Why? Basically, the question is, if that would be a scalar and is not different than zero, you can divide by it, but you cannot divide by vectors. Right? So what are you doing here? So because basically what I'm saying is this is equal to this. But I cannot just cancel the V. What am I doing here? It's just to be sure. Think about the step you make. Sometimes you're quick on this, but it's correct. But what am I doing here? Why can I do that?
Yes, you transform the force vector to the other bases.
No, look. Now what I mean is to say from here that this is true for every V and just get rid of the V. What I'm doing, if it's true for every V, okay, if I'm telling you, it's just a detail, but I just want to be precise because these things, are, let's say, matrix A times V is equal to matrix B times V. Okay? And I'm telling you for each V, then I can imply that A is equal to B. Why?
You bring V on the other side, and you get A minus B.
What V on the other side? How?
No. You bring BV on the other side. And it becomes
V on the other side.
BV. AV minus BV equal to 0.
Okay.
Okay, then you put in evidence V, you can.
Yes.
You get A minus B, V equals to 0. V cannot be equal to 0, hence A equal to B.
Yes, but you cannot say what about V? The V cannot be equal to 0. So of course can be equal to 0.
Okay.
It's a vector. I tell you, it's very simple. But just to let you think. Very simple. It can be anything. These are matrices, right? Okay, let me choose V equal to 1, 0, 0, 0, 0, 0. First columns are the same. Then I choose 0, 1, 0, 0, 0. The second column are the same. 0, 0, 1, 0, 0. That's it, right? If it's true for any V, it means it's true for any 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. So all the columns are the same. That's the reason you use it, okay? So I can do this. Now, you know, if I take the transpose of the product is the product of transpose, you invert the order, right? What do you see here? What is strange here? I changed coordinates, so you have the bar blue and you have the non-bar orange guys. Okay, these two guys here. So what do you see here? That I changed coordinates of the velocity like this from bar to non-bar, and the forces change in a different way. And look, the only hypothesis I started off everything I said that you guys should have the same power. And I concluded, I show you, because A and A transpose inverse are not the same in general. Okay, if I give you a matrix and you calculate the inverse that's transposed, it's not always the same as the matrix. When is that the case? When the matrix is, for example, a rotation matrix. Okay, is what is called an orthonormal matrix, which is defined when a matrix, the inverse is equal to the transpose. Are beautiful matrices because you need never to invert them. You just transpose it, you get the inverse. Okay, but this is a very special set of matrices. Okay, we will see in robotics again and again because our rotation matrices. Okay. But in general, this is not true. So why have I never seen this? Because in your education, in my education, they put you that I'll take an orthonormal coordinate system, and then you're just changing like this. So you always have rotation matrices. So only in that changes of coordinates, these two guys are the same, and therefore you never talk about it. But if you go to polar coordinates, forget it. It's not an orthonormal change of coordinates. Yeah. If you go to 6-dimensional vectors, we'll see a lot of cases, this is not true. This guy is different than that guy. So you see now straight in the face that velocities and forces are different objects because they don't change coordinate in the same way. So they cannot belong to the same space. Because if you change bases here, use this A. If you change bases here, use something different. It's as simple as this. Okay? And yet, they tell you that forces and velocity are vectors. Of course, they are vectors in their own vector space, but they are not the same space. Okay? You see this? This is as simple as crucial as important. Okay? The duality is here playing. You see straight in the face that forces are not the same as velocities. They change coordinates differently. If you change coordinates, you need to know whether one guy is a force or one guy is a velocity. Because they change differently. Okay? So velocity is a vector, a force is a covector, not a vector. Well, it is a vector, but in the dual space of the vector which velocity belongs. And the force is the linear operator from velocity to power. Yes, please.
If I looked at so far looking at vector spaces and their duality.
Yes.
With covectors, how do I choose that velocity is the vector, not forces the vector?
That's what I was asking before. You can, sure, in finite dimensional you can. In infinite dimensional is, look, there is something which is called involutivity. So if you take the dual of the dual, if it's finite dimensional, you get the same thing. So if I give you a vector space, you take the dual, you get another space. If you take the dual of the dual, you get the vector space you started off with.
My question mainly is that for our example with mechanical system, is there some, let's say...
Yes, so why, yes. So first the answer is, for talking about duality, it doesn't matter in finite dimensional. In infinite dimensional, it does. There is a closure issue. There are some strange things happening in infinite dimensional. But the choice why you choose velocity as a vector is because it's naturally when we go to infinite, when we go to nonlinear stuff, what you will see is that if I give you a sphere and you want to talk about the velocity of a plane on the Earth, right? you know, a position of the plane is definitely not a vector, right? It's a point on this sphere. And if you take a curve on this sphere in a certain moment of time, you can take what we'll see, the tangent vector. It's basically you have a tangent space of the sphere, and the velocity of the plane will be a vector in that point, at that moment, in that direction. Now you see that naturally, if you're on a curve and you move in a curve, and in this moment I'm going that direction, the intuition of in a nonlinear space, I'm moving in a certain direction, okay? And I want a representation of the speed by something which is the length, you know what I mean? It's not a length I can measure, but if it's long like this, as a certain speed, if it's long twice as much as twice the speed, okay, then it's natural to call this a vector. Because a vector is, you know, from an etymology of the word is a line with an arrow kind of thing that tells you the velocity. And that for that reason, you call that a vector space, and then the dual of the forces are dual vectors. That's the only reason. Yeah? Any other questions? Okay, now, subspaces. Okay, so subspaces are the basis objects of linear algebra, okay? So in robotics, you will see it all the time. You see it in solution of a linear equation. You see, it's a very, very, very fundamental concept, okay? So it's like, for example, and I will do this again and again. If I give you a linear equation, like, you know, y is equal to ax, okay? And then you say, suppose that A, I didn't tell you the size of A or whatever, okay, can be anything. If I say what x give you y equal to 0, you can see that that is a subspace. So any linear combination of objects to give you that are still solutions, okay? So if something gives you 0, you take another object that gives you 0. Any linear combination, of course, gives you 0 because this is linear, right? Okay. Well, that's called the kernel of that linear operator, for example, okay? In the set of all the elements you get as by taking any combination of x, what are possible y can you get? That's called the image, for example. Are all subspaces. So a subspace is basically nothing else. A vector subspace is that a subset of V is called a subspace that if you take any element in that set as a set, okay, and you take any real number, so you take any linear combination of anything there, you get something which is still there, basically. Okay, so again, this vector, you take a linear combination, so it's a plane. If I give you this vector and this vector, you know, the plane that they span is a subspace. Okay? And this, of course, and this is, of course, the same for dual vectors. So, you know, dual vector is again a vector space. Okay. So I can talk about subspaces of the dual vector, but are different, belonging in a different space. Okay. Now, annihilators. So yeah, you have I know, because it was a lecture of robotics. I talked about this yesterday also. Annihilator. So if I now give you, a plane, suppose I give you, this is the origin of my vector space, okay? And I have this plane. And I say, well, no, suppose that this is the point here, the bottom where the black is, let's say, is the origin of my vector space in this 3D thing. And I consider this as a subspace. So the plane, and it's not finishing here, the subspace goes to infinity, okay? Now, this is, of course, not the whole thing, because the whole thing is 3D. Now, can I define in a unique way something else based on this space? Okay, can I, for example, you would be tempted to say, well, if I have a space and I have a plane, I have an orthogonal complement, so I can define a line. But you don't have an inner product, so you don't have an orthogonal complement. Can you define something like that? Well, it turns out you can. But what you can do is on the other side, in the dual space. Okay, so if I have a plane here on a 3-dimensional space, I can define a one-dimensional space, which is in the dual space. Okay, are all the linear operators that apply to any of the vector on the plane. You see, I can do that because this is an operator on these guys. Okay. This linear operator on any element of the plane, it gives me 0. Okay, so I cannot give you, if I give you the plane in this space, I cannot give you a line here. I can't. There is no intrinsic way, if I don't have an inner product, to give you a line here, but I can give you a line there. And if this case would be, for example, this line here, the plane is not there. I only have to give you this line. I can define a plane here in the dual space, which is the set of all linear operators which apply to that line is equal to 0. Okay, so you see, it's very similar to dimension-wise to the orthogonal complement, but there's nothing to do with it. The formal definition is, which is a bit misleading, but this is what people use. The perp is not perpendicular, it's dual in this case. It says, if I give you a vector space and I give you a subspace A, the annihilator of this subspace A, okay, and which belongs in V, is something which belongs in V star on the other side, and is defined as the set of all linear operators that if you take any element of the subspace, it returns 0. Now, give me an example. Suppose I give you now a point which can move on this plane, a point mass, okay, point mass which moves on this plane. And I say, well, the mass can move like this on this plane, but cannot go anywhere else. Well, if it cannot go anywhere else, you know, what does it mean mechanically? There is a force that keeps my mass there. Okay, where does that force belong? Well, we know it's not a vector. Where does that belong? Belongs there. The force that keeps you there is a constraint. You know, for the D'Alembert principles, you know, constraint forces, ideally speaking, they do not create work. They just constrain the things. Okay, so if I give you this plane, I say the mass moves here. That means that the line I had here are the forces which keeps that, you know, they change in value. They can change in value, but are along the line which keeps that point on there. You see, so constraint forces, okay, are not, because we know now the forces are dual, and the annihilator of a set where you want to move is actually how the forces are in the dual space. Okay. And you can prove that these are theorems that if you have a vector space which is n, and you have a subspace which is k, the perp is n minus k. Okay, and if you take now the annihilator of the annihilator, you get the same thing. So it's involutive. So in other words, if I give you the plane, if I give you the annihilator is a line somewhere in the dual space, if I now say, what is the annihilator of this line? You get back the plane. Okay. It's involutive. Now, why is this important? Projectures. This is an absolutely fundamental concept used every single time in anything, but very likely in the wrong way. I'll show you why. Okay. There is no concept of orthogonality. In general, you do not have an inner product. This is the case I'm talking about now. And now if I tell you, I have this. What is the projection of V on AK? What is it? Could you tell me what the projection is of that vector on the red line? Yep. Yep. This is a non-defined well problem. You cannot say. How do you define projector? Tell me. You cannot define. If I give you this vector space and you do not have an inner product, you know, I could draw this like this. You have no conception of what means going down the vector. But you see, we are so bounded by thinking that you always have a an inner product that you just not even think about it. This is not a well-defined problem. Okay, because the answer you gave me is true if I give you an inner product and if I tell you that this vector is orthogonal to that line for the inner product that you want to use. And then you can say, okay, take the projection, blah, 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 the orthogonal projection, blah, blah, blah. The correct way of doing it is, in general, for a vector space, you can do that. But then you need to define a concept which is called the direct sum. So what you have, if you have a vector space, you can define a complementary vector space. What I do, suppose I give you this plane. And now I tell you, I give you another line. But I choose the line. You know, the line could be like this, as long as the line is not in the plane and it gets out of the plane, is complementary to that space. So then I can uniquely describe any vector as unique sum of a vector which belongs to this one and a vector which belongs to the plane. So in other words, I can split the space I have in two subspaces, okay, which are complementary, which means that I can split it such that any vector that I have, I can write it as a vector sum of one unique guy here plus one unique guy there. Okay, so here we'll read the definition. For each vector that you give me in the vector space, there exists a unique, this is simple, there is a unique, there's no choice, there's one guy, okay, A in A, and there is a unique B in B, such that the vector you give me can be written like that. That's the definition. So what does that mean? Well, it means that if I give you a three-dimensional space and I give you the plane, you cannot decompose anything yet, but if I give you any line out of this plane, through the origin, of course, okay, which is not on the plane, then you can always write, then you give me a vector, this vector, you can then uniquely write that vector as a sum of a vector on the line, the vector on the plane. No inner product. I'm not using inner product. There's no structure. Okay. And now, okay, I can talk about projection. Now I can say that A is the projection of B along the dual space I defined, right? Or the other way around. So now if I look at the problem and I say, what is the projection of V on A? It's not defined, but if I say along B, then it's properly defined. And now, what is the answer now? What is the projection of V on A along B? Just use the definition. Okay, so you just say, okay, I give you two complementary subspaces. Okay, this is a two-dimensional vector space. Okay, so you have two subspaces, the red and the blue line. Okay, so the only thing I need to do is to write that vector, black vector, as the sum of an element on the blue and a black line. And if I do, I use the parallelogram rule. Okay, that's the only definition. Now, the projection of V on the red line along the blue line is this guy. That's the projection. Okay, because V is equal to A, the answer is A. That is the proper definition. So it's not the origin. Now, if I would give you and tell you, and I would have chosen, of course, I didn't choose it on purpose, the blue line, by any chance, like this, you would have gotten zero. In that, well, you would have got that thing by any chance. But if there is no inner product, this line is not more beautiful than this line or this line or this line, or infinitesimally closer to the other line. It's the same. There is no difference whatsoever. Because there is no concept of inner product. There is no concept of orthogonality. So what you do all the time is that if there is a concept of orthogonality, you do precisely what I told you now. But you define implicitly the blue line as an orthogonal complement to the red one. And then you do what I told you. But you see, it's an extra thing that you do implicitly. So if I give you in general, and this happens a lot, believe me, a space which you want to treat, the physics right, and not say, oh, I have an inner product if nobody gave you, and there is no physical reason why for you to have one. If you want to do projection, if I tell you what is the projection on this subspace, it's not defined. You'd have to tell me with respect to what other subcomplementary subspace. Okay, is that clear? The projection is very important. This is a concept which is done so incredibly many times wrongly. An example in robotics, okay? I give you in biomechanics, robotics, whatever you want. I have these arms. Suppose I have these degrees of freedom, okay? If I would just chop my arm here, I have this part of my arm is a rigid body, roughly speaking, okay? How many degrees of freedom has a rigid body? 6, right? 3 translations, 3 rotations, okay? So I can describe the infinitesimal motion. You will see precisely how to do it as a vector space, using a vector space, which is happen to be a Lie algebra, which is 6-dimensional. Infinitesimally, any possible velocity you could describe with 6 numbers, so to speak, okay? The same you can do with the upper arm. But now I connect the two as it is now. So I have 1 degree of freedom. So I say, oh, that's good. So I can represent the possible velocities of these two bodies as one rotation around this. That's one direction. Okay. All right, that's nice. So I had 6 degrees of freedom. Suppose this is fixed, it's not moving for the shoulder. Okay. So now I have 1 degree of freedom, but I know I had 6. So I lost 5. Can I just choose them like that? So you say, well, you take the ortho. No, you don't have orthogonality. Unfortunately, you can prove mathematically that for a rotational rigid body, you don't have orthogonality. So what the hell do you do? Okay. What you then can do is to tell me where you actuate. That's the next thing we'll see properly, because you can say, okay, then if you have now, the only thing I can tell you if I knows these degrees of freedom, what have you learned before? What I can tell you, if I tell you, I have a 6-dimensional space, vector space of all possible motion of a rigid body, and I give you a 1-dimensional subspace. What can you give me for free without any other thing?
The subspace of the other 5.
Yes, you can give me a 5-dimensional subspace of forces. Okay, very good. What are those forces?
The one keeping you fixed.
Constrained. Very good. Very, very good. All right. That's the only thing you can say. And now, how can you handle if you want to put an actuator? What do? You define the other force on the other side. I gave you 5 by the constraints. I need 1. I need to define another one, which is complementary to this. Can be anything. You see? Now, suppose I give you now my arm, a force which applies in the muscle attached from here to here. Well, my muscle is attached there, but suppose you open up my skin and the muscle is attached there. You can describe that force very precisely in what we will see. So it will give you a force that indeed, if you apply that force, it will move. It will transfer power to that motion. That force is not in the same place because by definition, the 5-dimensional dimension creates no work, doesn't move. But this one does because I built it in that way, right? I give you this. Now, what can I do now? If I now have one force that I defined, what can I do now? Play the same game you just played, but the other way around.
Basically,
I can define a 5-dimensional subspace in velocities, which create no work with this. Aha. And that now is what I needed. So I have 1, and now I have the other 5. That is the correct way of talking about constraints. Okay. So now let's try to formalize this. So if I have now a vector space, and I have a subspace of dimension k, I can, and I have other vectors, you can kind of split it by choosing the basis. So for example, I choose 1 here, and then the other 5 you just choose. You tell me what the 2 subspaces are, and you complement them, okay? And then, and these are just things, I don't want to go to the details. You can try to look at it. The point is what I just give you in the example. It is possible to basically split the dual space in something which is such that this dimension is the same as this dimension, it's complementary. So in the example I gave you, this would be 6, this would be 1, this would be the velocity of the joints that I have, this would be the torque that I apply and it produces power there, which really creates motion. This would be velocities that are not there. Okay, and this would be the constraints forces that keep you that. And this split in this way, you can uniquely identify only if you give me either this and this, because if you have this with an annihilator, you define this. If I give you this with an annihilator, you define this. Or you can give me this too. Okay, or you can give me, as an example I gave you the degrees of freedom, and I told you what the force that I apply. If I give you this and this, well, you take the annihilator of this, you get this, you see the game? Okay? And this, I guarantee you, this is not properly clarified anywhere, except in the things I write, but this is something, is a detail, which is important. Certainly if you want to do invariant calculation. And then you can define operators, as formally as I define project on one subspace with long the other, and there are certain properties that says, well, this is the definition of a projector. Projector is actually in quantum mechanics, for example, is a linear operator that is, if you take the square of that operator, you get the same operator as a projector. You can prove all these things. It's not so important at this stage. But this is the core, and this is basically the things I just said in more formal terms, that you can choose either one and you calculate the other, the four things that I said before. All right. Let's have a break for 5-10 minutes. Then we go to the something important in robotics. Then you will understand what the transport Jacobian actually is in a proper terms.
So we had
Legitimate.
a sort of pre-conversation before. What was that?
Question is now,
Was working on segmentation.
if I have a linear map, can I uniquely define another object without any extra structure? So I give you two vector spaces, and I give you a linear map between these two vector spaces. The question is, can you define something else? But then intrinsically, you see, I stress it again and again, I give you something. What can you talk about without adding any artificial things that just came out from heaven or something? Okay. What can you do? Well, it turns out that it's possible to define, again, duality, a new map, okay, which is called the adjoint or dual, that map. And this is true also for a nonlinear system. Okay, it's just for infinite dimensional system, which is such that you see this other map, it goes in the opposite direction. Okay, so if this map goes from V to VW, the other map goes from the dual of this one back, and is defined in such a way that what can you do if I give you an element here and an element here? You can let them kiss each other, right? And give a real number, velocity, force, power. Okay, and you want that this power is equal to this power. Obvious. Okay, so what I'm saying is, if I give you a map between two linear spaces, what have you learned so far? So I give you a linear space, you have a dual of a linear space. Okay, dual of a linear space, and you have a dual of a linear space there. What can you do now? Well, it says, well, if you give me a dual, I know that if I take what are duals, are linear operators on velocity. So if you give me a vector space, velocities, I know that there is a space of forces which are linear operator on that to power. So you can then define basically, and you will see actually it's the same thing. It's even worse. There is no, this guy is the same as this. We'll see that, what I mean with that. But you see, then basically you say, if I have a V, okay, a V in V, okay, and I have L of V, then it means that if I take a dual there, you shift, the L on the other side, so to speak. But what this actually says is nothing else that if you take an element here, you map an element there, the other map should be such that if you choose anything here and you have a certain power, the elements that this map should give you should have the same power. Okay. Well, this is, we'll see it, a transformer. It is an object, but now precisely defined, which basically is power preserving. Okay, and I define that just only defining this. This is just given automatically. In robotics, for example, we will see this will be the Jacobian. The Jacobian transpose is just the same thing. is the adjoint of this. There's no other thing. It's, it's a natural things because you want to preserve power. Okay. Yes.
You could also ask the same question, but then have the lower arrows pointing from left to right.
Yes.
Could be the same question, or
Why
do you do it in this way?
Very simple. Suppose I give you now first finite dimensional. Suppose I give you now this space is 2-dimensional and this space is 10-dimensional. Okay.
Yeah.
How would this matrix look like? Because this is a linear operator. If I choose basis, I can write it as a matrix, right? This would be a matrix which is 2 times 10. Can you invert it?
No.
There you go. You can transpose it. This guy. So if I give you a matrix, and this is something we'll see also very well. If I give you a matrix as a representation of a linear operator, okay, you know that the matrix is, now you understand that the matrix is more than just numbers. Suppose that that matrix represents a linear map. The transpose of that matrix is something that represents a map of the dual space in the opposite direction. Okay, and I'll show you properly, in my opinion. I've never seen it written like this because I think it's the first time I wrote it down properly. There is a very famous theorem that you must have seen at least once. You probably forgot, but you definitely have seen that there says if I give you a matrix A, and I say, well, what is it? The kernel of A is equal to orthogonal complex of the image of A transpose. Okay, it's something, it's a basic theorem of linear algebra, which is not true, stipulated like this. I'll give you the correct way of saying for following the proper mathematics, okay? So, in other words, if I give you a matrix, you cannot do what you're saying, guys, because this 2-dimensional, not even, this could be infinite dimensional. And this could be finite dimensional. I give you an example. Suppose actually something I did a new. If you have suppose I have a sphere. I have a sphere, and I will be able to talk about the velocities of this sphere because it's a sphere. It's a 6-dimensional. It's a rigid body. Okay, as six velocities, rotation and translation. Okay. Now I could say I want now. If I give you this velocity, I want the vector field on the sphere that tells me how this point moves. Why would you do that? Suppose that this sphere is in a fluid. Okay, it's in a fluid, so this sphere rotates. And in this point, every point, of course, has a certain velocity, right? So, and of course, a vector field on the sphere is infinite dimension. It's a vector field. Okay, that's a linear map. Okay, it's a linear map between a 6-dimensional vector space and an infinite dimensional vector space. So this would be the twist of the body, the velocity of the rigid body. And this would be the vector field. Okay, you cannot definitely invert that, but what you can do, if you give me a set of pressures on the sphere, you integrate them on the sphere, you can give me the wrench, which is the result of what happens if that is in the fluid. You see, it's natural, it's obvious. So if you can always do this just by saying physically, if I have a boat on the sea, a boat on the sea is a rigid body. There are a lot of ways. There's fluid dynamics moving around, but the way that moves as a rigid body. Now, of course, all the points for this is called no zero slip condition in fluid dynamics. Every point of touching the water will have a certain velocity interacting with the fluid, right? And what is the total force that keeps the thing where it is? Well, it's the integral of all the forces where the pressures of the thing is. This is it. Orientational motion of the boat as a rigid body, vector fields of the points of the water, pressures on which is dual, and the integral is the power that is exchanged, which should be the same. as this. This is true for any infinite finite dimensional space. You cannot invert the map. And the point is, I was saying actually yesterday to the students, going to teach you this, you know, in robotics, this is done all the time. People, I almost killed somebody when I was a student because, you know, controller were done in a shitty way. If you invert the matrix and it is not invertible, you should ask yourself what you are doing. Okay? If that matrix could lose rank and could become singular, okay, and then you say, oh, you know, I'll try to stay away from that point. Well, probably you should start away from everything you're trying to do it in that way. Okay, because the fact that you cannot invert it somewhere, it means that what you're doing is not the way you should solve your problem. Okay, and you know, inverting the kinematics is something which I never done, I will never do, and I have reasons for that. Okay, because inverting kinematics is not something you should do. There are much better way to do it. That's what not we do. When we interact with the world, we don't invert kinematics. We use a transpose Jacobian. Because if I want to do a control on a nonlinear system, a robot manipulator, I can have a very complicated thing. But if I now attach a spring to this hand, and I have a spring and I pull the spring around, okay, and I control it like this, what I do, basically say, okay, I know where my hand is because I know the joint. So I have the direct kinematics, a function. We'll talk about all these things. I can calculate the force that spring, which is not there, it's just in my mind, okay, for control. I can calculate easily what the force would be that spring would apply here. If I have that force, which would be here, I can calculate the force on all my joints. I implement it, and that is never going to have any problem with singularity. That's the way you should do it, because that's the way physics works. But in robotics, people forget about nature and they think I have equations, so they just forget the nature. And then they do things and say, oh, there is a singularity. So let's do something, a vector field that keeps me out of that singularity. So blah, 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 blah. Do it right first. That's my opinion. Is this clear? Yes, please.
There's a question online, which is said by Paulo.
Yes.
That this concept is real representation.
Sorry, is
representation.
no. Okay, there is a presentation. Excuse me. Okay, what is the risk representation first? The risk representation is a theorem, basically tells you that if you have an inner product, okay, which we don't now, if you have an inner product, then you have a one-to-one relation basically between vectors and covectors. But explicitly, I'm saying we don't have it yet. Okay, so I really want to talk about the concepts and then add the structure so that you recognize once you do something, if you use the things that you have or you don't. Okay, the problem is, for example, if you look at rigid bodies, okay, because I think you can prove. Actually, it's easy to prove that for rigid bodies, there is not an inner product. Full stop. You can't, does not exist an inner product. You can define it and you can fantasize about it, but there's not a physical intrinsic inner product. And it's very deep because the reasons is because the motion is a certain group, which is called not semi-simple, and therefore it does not have an inner product. Full stop. That's it. So in that case, and this was something that in the 80s was very famous problem. When I started doing my graduation, was called the fallacy, where there were people doing hybrid position force control. This is interesting. If I give you the plane, people were saying, okay, I use hybrid position force control, which means I touch this table and then I do force control on the table and I do position control in all directions where I can move. But this is rigid body, 6 degrees of freedom. So they were saying, okay, you know what? Let's choose a base. And then we say, I define this as a space I can move. And then I define the orthogonal complement where I can motion the forces. Too bad that forces are not in the same space, so you cannot talk about it. And then some people are using coordinates will say, oh, you get a different result than me. How comes? blue, orange. Okay. And then there was Duffy and Lipking and wrote his famous papers, The Fallacy of Hybrid Position Force Control. And basically they say, guys, sorry, but there is no inner product. So you can't do that. Okay. And unbelievably enough, there are now a lot of even senior professors that are not aware about this result in robotics. So it's answered. Is it happy with my answer?
Yes, he says, thanks, I didn't remember the necessity of metric.
Yeah. So the risk representation theorem is and that is actually what you use in quantum mechanics all the time. Because in quantum mechanics, you are given a Hilbert structure. Okay, and basically you say if you have a bra, you have a cat, you actually have this. So if I give you a cat, I give you a bra. If I give you a bra, I give you a cat. The fact that I give you a vector, you can give me uniquely a covector. That is risk representation theorem. Okay, now tensors. Now we are able to do everything. So look, now you know enough, because now you know that everything we will build is on vector space. So if I give you a vector space, you have a dual of vector space. Now you understand the difference between the two. And now, well, you can say, okay, if I give you now a matrix, which would be a map, right? And normally if I give you a matrix, forget about what I told, give you a matrix, I give you two arrays, you can give me a real number. Now what you can ask yourself is, okay, I give you a matrix, it takes two vectors, okay, two array of numbers, return me, but now you know, say, wait a minute, is this guy here a vector or covector? On the other side, is this guy a vector or covector? And then on the basis of that, how many possibilities you have for a matrix? You see, you can have two indices like this, two indices like this, two indices like this, two indices this. Okay, you have four possibilities. So if I give you a matrix now, the question is, what does that represent? Does it represent this or that? Okay. So what is a tensor? It's not a matrix, higher dimension. No. The definition of a tensor of type PQ, this is called the covariant and variant. Variant and covariant is the index. So, okay, let me tell you later. So this is here. You see, a vector is a tensor of type 1, 0, for example, and a covector is a tensor of type 0, 1. You see, just mnemonically, what did I put the index of the numbers up? If you have one index up, is a vector. If you have one index down, is a covector. Okay. Formally, let's first formally. What is a tensor of type PQ? It is a multilinear operator, okay, that eats Q times V and eats P times V star. And it spits out what? A real number. Because we are in the real field. For complex, you should be C. Okay. Now, do you see what a covector was? The definition of covector was where P was equal to 0 and Q was equal to 1. You see? But now I feed him with more of these guys, and I make it different when this one is a vector, one is a covector. And then you also can see, and that was Gijs, you know, these things I was doing. Now you can say, well, a vector can be seen as a linear operator that eats one covector and spits R. Okay, duality. And then you say, and this is not nomenclature, you say, well, the rank of the tensor is the sum of P and Q. So a matrix is a representation of a second order tensor. But in mechanics, in continuous mechanics, stress and strain, okay, are much bigger because you have the stress, for example, is a second order tensor. Well, green stress depends what stress you define. And the strain could be a second order tensor. So if you want to have a Hooke's law, you need a fourth order tensor that maps these two indices to these two indices. But we will not go to that, but I can, you will understand then all these things now. All right, now, so let's see this. Suppose that now I have this map. So I say, well, a 1, 1, 0, 2, 2, 0. Well, this is a map that takes one vector, one covector, and return a real number. Okay, and I call this an endomorphism. Why? Because it's the same as this. You don't see it immediately. You will see it in a moment. That is precisely the same thing. Well, what is, well, this you recognize it. You know, if I give you two vectors and you return a real number, it's called a quadratic form, right? An example of that would be kinetic coenergy, right? I give you half what you would write with this, like this, okay? And the half, you just put it in them, so to speak, okay? So you see, two vectors. How would you write this in text? Now you know. You would write it as m, half, okay, half, m, ij, vi, vj. And there are two sums here you don't see. You see immediately now that if I give you two vectors with two indices up, if you want to give me a real number, which you call kinetic energy, you need to give me an object which is multilinear and has two indices down. So it's a 0, 2 tensor. So if I give you two vectors, two 1, 0 tensors, the only way to give me something that makes any sense, physically speaking, as a real value, in this case, kinetic coenergy, okay, you need to give me something that can contract these two indices, but needs to be down. So it's a 0, 2 tensor. It's a guy like this. It takes two velocities and returns a real number. This would do the opposite. This would be a guy who eats two forces that gives you a real number, right? Now, what is this guy? Why is this looking like this? Well, I'll show you in a moment. So, linear map, this guy. Look, I'm telling you that this is the same as this. Why is that? Well, V can be seen as a linear map from V star to R. That's what Gijs was saying, right? So I can give you a vector can be seen as a map from forces to power, right? This duality stuff. So if I give you a matrix P, which is maps to V, you know, a linear map. You see, this is a linear map. Actually, is a what is called the endomorphism. It's a map on the same space. So from V to V, okay, where eigenvalues makes any sense by any sense. Okay, if you do it like this. Look, what you can say, well, this is a vector, right? So if I have a vector, I could pair it with a force, so with a covector, okay? And these things would be a real number, okay? So you see what I can then do, I can use this. I can say, well, I give you a velocity and a force, okay? And multiply the V times B, I get this W. And then what is left, I multiply it on the level force to give the real number. Okay, so you see that saying that you have that these things here, okay, as an index up and an index down is a linear map, but you can also see it from the rotation because now, look, if I now give you, and I say, I have this tensor, oops, Ij, okay. What can you tell me? Well, you can tell me it's a 1, 1 tensor, okay? Which means you can represent it with a matrix with these two indices, okay? Now, what can you do with these guys? Well, has two indices, right? I can contract it with something. Okay, so it has two indices, so I can contract it with a force and a velocity, right? This is what I did here. And I could do, for example, say, I give a velocity, I, there is the sum here I don't write. And then this is what is left, right? And then I just use Fj, then you have a real number. Okay. But I could also say, well, I don't do this. I just write it like this. What do you get? Well, I take the sum on the i's. The j is still free. I haven't done anything with the j. What do you get? You're left with that thing. This object has one index, you can write it like this. What do you recognize? This is a vector. So this is a linear operator because it goes from a vector to a vector. You see the game? Yeah. So I didn't write the sum, but if I write the sum, you recognize it easily. If I write here sum of I that goes from 1 to 3, for example, that is just the way you write the matrix multiplication. Okay. But you see from the indices that I now, boom, I can tell you what that guy is. If I give you something like this, I know that I can use it like this. But you see something more. If I give you this, is there another way I can use this guy? I contracted this index, but there is another index. So what can I do?
Okay.
But you know, it needs to be a force, right? If I have here Fj, you get here, let's say, another guy, which is left here, right? What is this guy? They are joined. You see, it's the same thing. I haven't changed anything. This is the same thing. So I define it as a map, but it's the same nature. It's the same thing. It's just a physical multilinear object, which I can use it like this or like this. This is cool, huh? Because you know, normally you say, "Oh, I have a map and I define the adjoint." Yes, you can define it as a map is a different map, properly speaking. But the nature of the bloody multilinear thing is the same. It's the same thing. I haven't changed anything. I just contracted different indices. Okay. And then you can also say, good, when can I talk about eigenvalues, for example? Well, here I definitely can, because I can ask something here. Well, I could also define of the dual space, but if I give you this linear map, okay, I know that you are left with the vector again. So I can ask myself when I can write it something like this. Well, and then the V's that satisfy, I call that eigenvalue, eigenvectors, and the lambda that's respect, I call the eigenvalue. I cannot do it here. If I give you a mass, Mij, okay, and I multiply it for a vector, excuse me, I can contract one index, I, what am I left with? Not a vector. So I cannot say is the same vector here times something. It makes no sense. People have done it all the time. What is this guy, by the way? Do you know what that guy is? There's an index down, that's for sure. What is this? This is a mass and this is a velocity. Momentum. The momentum is a dual vector. It's not a velocity. And in fact, we know from Newton's law, Newton's law is this. Okay. Yes, you have a question, somebody. Yes.
So what you mentioned, eigenvalues of a matrix mass or inertia matrix.
Yes.
I've seen this. You've probably seen this as well.
I've seen it and got shivers again and again. Yes.
So if it sometimes it's used for analysis. So
it's shitty analysis.
So the analysis output is wrong. So
it's simply wrong.
Yes.
I'll give you an example. There is something in robotics that people, there's a guy I will not name it. There are people that have spent their life in talking about manipulability in robotics. Is conceptually, structurally a wrong concept. I published a paper with one of my PhD students on the Journal of Robotics Research, trying to be political about this, and people probably don't even see it, but it's structurally, conceptually wrong. And the reasons for that is very simple. If what you do is you take the Jacobian and the transpose of the Jacobian. A Jacobian, well, some people don't know what a Jacobian is yet, will come clear. It's a map between the vector spaces. The transpose is the adjoint, is maps the dual. So you have between the Jacobian and Jacobian transpose, magically, you go from a vector to a covector. What can you do? When can you do that? If you have a metric that does that. But in general, definitely, if you want to talk about manipulability over what there is by, it has been proven that there does not exist an intrinsic metric. So kinematically, it makes no sense whatsoever to talk about that. If you put dynamics in the game, then you can tell me, okay, the inertia tensor, which represent the dynamics of the robot, and then you can do something about it. But still, there are a lot of problems. We'll talk about that.
Because most of the time, in robotics, they can show you in the published paper that it works, and then you should believe that it works.
No.
But
It works. It just works. You change the coordinates, you get different numbers. So it's bad work. It's just bad work. Okay. And it's like people that you can do a lot of things that you finally manage to work, but conceptually is wrong. No discussion about it. It's conceptually wrong. Because if you change manipulability, I show you that this is like this. Now I say, okay, I change coordinates. And the ellipsoid was like this, and now it's orthogonal to that ellipsoid. I can. If I can find, I can give you coordinates which completely cancel, completely orthogonally tell you something different. And then you show things that said, it's working. It makes no sense. Now, I hope you start for these comments to understand how important this stuff is. Because, there are a lot of roboticists that just, think they know better, that they don't. And this is, this is standard known mathematics for ages. Okay. Yes.
But just to ask there, no, you brought WV in V, but it's not correct, right?
Where?
W, comma V. Yes, there.
Yes.
Because you are.
That's correct.
But you're meaning the components.
Yeah, sure. Correct. So what I mean, I've been sloppy. I've been very sloppy. This is a representation of object here. I'm not belonging here. Yes, absolutely. These are well, I could be saying, well, no, I am correct because B is a linear operator. Actually, no, it is correct.
Why?
it's endomorphism.
Because this is a map. I'm not talking about coordinate anywhere. Well, here, this is misleading. This is misleading. If I would substitute this with this things, then it would be correct. Yeah, it's true. So the only thing I should change here is to write the dual pairing, then it would be coordinate invariant. Yes. Yeah, but a point taken. It's a good point. Yeah.
Is that the comment you?
Yes,
Okay.
that one.
Okay, let me, time is up, but I just want to see whether I can give you the last things and we close this option. The issue, if you have a linear map, you see, if you take a linear map with different coordinates, that the orange and the blue, you see that eventually the way you change coordinates is like this. So you have on the right and on the left, matrix and the inverse. Now you see immediately, you use it all the time. This is what you do in linear differential equations. If I give you a linear differential equation, and I say x dot is equal to ax, and you want to change coordinates in the state space, okay, you can write it as z dot is equal to a bar z, okay, when you define that z, for example, is a certain change of coordinates with respect to x, and then the change of coordinates with respect to that group. Okay. So indeed, that's why in linear system theory, it makes sense to calculate the eigenvalue, which are called poles and blah, 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 blah. Okay. So that is correct for this reason. And in fact, the representation used is just numerical representation. The concept of state is independent. If you choose z of x, it should be the same. But on the other hand, if you have quadratic forms, okay, the change of coordinates, you get a transpose. Transpose inverse are not always the same. Only the same if you use orthogonal changes. Okay, and then you have to be careful. And this is the issue of the eigenvalue. Okay, you cannot talk about eigenvalues if you are not a linear operator. It makes just no sense. Inertial matrices, eigenvalues equal to shit. You can't do that. It makes no sense. Okay, and for these reasons, these are the notations. So you see index up, vector component, forces. This is the metric, for example, inertia or things like that. And we'll see it next time. Yeah, any closing questions? We will not go further than second order tensor, but I mean, it's the same. It's nothing changes. You know, I could give you something with for example, in stress, I believe, you know, you have things like this. If F is Kx, okay, Hooke's law. Okay, if you want to talk about stress, usually I think the stress, depending what kind of stress you use, you can say something like Ij, and then you have strain that could be something like Ij, for example. Sorry, Lk. Lk. Okay, there's a second order. So what is the respective of this law? What is Hooke's law? It's clear, right? It will be something like the K will be a fourth order tensor in which it returns Ij and it needs to contract KL. You see, it's boom, you have it, it's clear, it cannot be anything else. If it's a linear relation, should be physical, should be tensor invariant, this is what you should get. Yeah? Any questions?